Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are touching our lives and changing the way we view the universe. And with us today is Professor Jana Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, author of a number of great books, including How the Universe Got Its Spots and Black Hole Blues and Other Songs from Outer Space. But today, we'll be talking about her latest PBS television series, Black Hole Apocalypse. So we'll be talking about black holes in this hour. With us today, we're very honored to have with us Professor Jana Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, right here in New York City. And she's the host of Black Hole Apocalypse, a PBS TV series that's debuting right now. And we should also point out that she got her bachelor's degree at Barnard College. Her PhD was from MIT. And once again, she's Professor of Physics and Astronomy right here in New York. So, Jana, let's get right into it. When you were a young child, what was it that steered you in the direction of science and then physics?
I wasn't one of those kids that always thought I'd do science. I really didn't have that consciousness at all. And looking back, I can see all the signs, but somehow it didn't add up to me that I would become a scientist. I really didn't consider that until college. Until halfway through college, I kind of discovered physics. I was a philosophy major, and I was studying the canon, and I really got frustrated with an approach to answering questions that I thought was so rooted in an individual personality. We kept mining these individuals over history, and I became really enamored of thinking about Einstein. When Einstein gave us relativity, it really was a gift. We didn't go on and on about what did Einstein mean. We knew exactly what he meant once he offered it to us. And I was really thrilled by that, by the power of answering questions in physics. And I just very quickly sort of did this radical change in direction and started studying astronomy and physics.
Okay, and one of the most preposterous of Einstein's predictions, a prediction that was so preposterous that he himself couldn't quite get his head around, is the black hole, the subject of your new PBS series. So first question is, I should say that it's a film. So it's a 2-hour special, The Black Hole Apocalypse. Okay. Well, first of all, what is a black hole?
Well, so a lot of people do think Einstein discovered all of these incredible implications of his general theory of relativity, but Einstein didn't discover the black hole. It was discovered by a friend of his, Carl Schwarzschild, who was a German astronomer and was reading Einstein's latest publication during the war, World War I, while he was actually on the Russian front. And within the span of a very few months, very quickly, solved in Einstein's new theory of curved spacetime this radically peculiar solution, which we now call a black hole, but at the time didn't earn the name for decades. And what Schwarzschild found was that if he just imagined, he didn't ask how nature might do it, but if he just imagined that you took, let's say, the mass of the entire sun, and you crushed it to a point, how would space and time curve around it? And what he discovered was that there would be a region around this crushed mass that was so strongly curved that not even light could escape, and everyone uses that phrase, a region beyond which not even light can escape, and that's what we call the event horizon. And to a large extent, that really defines the black hole. The black hole is a region of curvature in space and time so strong that not even light can escape, and so it becomes dark. Any light that transits too close just falls in. Any object that transits too close just falls in, and all the black hole can possibly amount to after that is just a shadow on the sky.
Okay, well, apparently Einstein himself couldn't get himself to believe that nature could create a black hole, because you have to have such extreme conditions. But wasn't it
exactly.
Professor Oppenheimer, the one who actually showed how nature could create a black hole? So how do you create a black hole?
Yeah, exactly. Einstein thought this was a brilliant solution from Karl Schwarzschild, but he didn't believe nature could possibly figure out a way to crush all that matter down to a point. I mean, after all, it's very hard to crush matter. The sun is a big object. It's huge. It's not a collapsed, tiny little thing. And so Einstein really dismissed it as a mathematical oddity, but not something that would occur in nature. And it really wasn't until people like Oppenheimer, who were very invested in nuclear physics, because in no small part they were interested in the implications of nuclear physics for the Manhattan Project and for the first nuclear bombs. And in the process of understanding the fundamental behavior of particles in the nucleus, they realized that even though it seems like it would be very, very hard, and it is indeed very hard, to crush nuclear matter because of the nuclear forces, they realized that if a star ran out of this nuclear fuel, which kept it burning and bright, that it would indeed collapse under its own weight due to gravity and overcome those nuclear forces and create a black hole. And many people believe that was Oppenheimer's finest contribution to physics.
And some people, children of course, ask the question, will our sun one day become a black hole? I guess the answer is no. You would have to crush it down to about 2 miles, I understand, and that's not going to happen. Mm-hmm. But in outer space, we see these things, right?
Yeah, so the sun isn't quite heavy enough. The sun will run out of nuclear fuel, will stop shining the way it is now, and it will go through a kind of death throes. And in the process, it won't be so good for us either. Might be better for it to become a black hole. It'll kind of vaporize the inner planets and go through its death throes. But if it was heavier than the sun, maybe 10 times heavier than the sun, then it can collapse under its own weight enough to overcome those nuclear forces and become a black hole. And we actually see evidence since the 60s and 70s of black holes in our own galaxy, not that far away. A few thousand light years. In the scheme of things, that's not far away.
Okay. And every kid who goes to a planetarium and realizes that these black holes are quite mysterious wonders what happens as you approach it. So let's say you're in a hypothetical rocket ship. Oh, we have to take a short commercial break now.
I'm on the rocket ship.
All right. But after the break, we'll talk about what happens when you approach a black hole. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Jana Levin, host of Black Hole Apocalypse. Watch for it on PBS. So, Jana, where we left off, we were talking about what happens as you approach a black hole in a rocket ship. For those people who saw the movie Interstellar, we got a computer simulation of that. But run through the steps of what happens as you get closer and closer to a black hole.
Well, it is extraordinary that we can kind of visualize what it means for a black hole to curve space, but it's much harder to think of its effect on time, on space-time. And in some sense, that's the most profound effect you would experience. If you were in a rocket ship and you were traveling to a black hole, what you might see is a kind of shadow cast on the sky. So let's say you were looking in a particularly bright direction of the Milky Way galaxy where there were lots of distant stars. The black hole would simply be a shadow against those stars. And as you move towards the black hole, you would, in some sense, not find anything that peculiar, but you would see all of those distant stars very distorted. And the closer you got to the black hole, let's say you were keeping in touch with somebody back far in some space station, far from the black hole, they would perceive you as slowing down. They would perceive your biological clocks, your mechanical clocks, your digital clocks, everything on your spaceship to be running slowly, all in sync together, but slow compared to the clocks on their own spaceship. And the closer you got to the black hole, the slower and slower time would seem to progress for you, so that you might age, an hour, and somebody back at the space station far away might age 50 years. And this radical ability to experience the relativity of time is one of the most peculiar things about a black hole. As you approach the event horizon, you would appear to freeze. There would be a sort of a last signal that you would send out back to your companions in their safer space station, and millennia would begin to pass in the rest of the universe. And so you, in some sense, travel to their future, not your own future, but their future. Now, from your perspective in the rocket ship, nothing odd is happening at all. Everyone far away seems to be speeding up, and civilizations are coming and going, and you're just drifting across this kind of ordinary shadow, almost like you were walking into the shadow of a tree. It's really not peculiar at all. Unfortunately, you'd only have a few microseconds to live after that transition to the interior of a black hole, where things get very bleak.
One problem, right?
Crushed to death. Yeah, that's a real problem.
Now, just before you're crushed to death, some people have talked about spaghettification. So what is it when your body becomes spaghetti?
Well, so the closer you get to the center of the black hole, the stronger the pull on your feet relative to your head, and so you literally become pulled apart. You also become kind of crushed because you start to feel this squeezing as you get closer and closer to this extreme curvature in the center of the black hole, which some people think might be a true singularity, an infinite curvature, an infinite space-time deformed region. And so you become spaghettified. You basically are stretched out as thin as a noodle, and eventually ruptured into your fundamental particles. And all of that debris falls into the singularity, and we don't know what happens after that.
Okay, well, let's talk about that because, of course, there's a movie, Interstellar, where they go through different wormholes and into parallel universes. But first of all, let me preface the fact that I guess we physicists are clueless. We don't really know for sure what happens. But what are some of the theories, as you go through the event horizon?
So after you go through the event horizon and you're plummeting towards the singularity, which is completely inevitable. There's nothing you can do to avoid the singularity. In some sense, space and time have switched places inside the black hole. So the singularity is actually in your future. So you can no more avoid it than you could avoid the next second in the flow of time. And so inevitably you go towards that singularity. Now, some people think that maybe you're blown out of that singularity into a new Big Bang, that each particle that falls through becomes part of a new ecosystem in a new universe. So the black hole might be... A
new white hole, right?
The white hole, right. A white hole. So it's the opposite. Nothing can come backwards into the white hole, but everything comes out. It's really the opposite of a black hole. And in some sense, the black hole might be, let's just say, a few kilometers on the outside across, but it could be as big as a universe on the inside. I love that idea. It's a beautiful idea, but theoretically there are a lot of problems with it, and people think it would make the universe unstable in some way. And so, other ideas are that there's a quantum remnant, like a smaller than microscopic, smaller than we're used to thinking about by many orders of magnitude, a little rock that keeps a remnant of everything that fell into the black hole. And that's also become quite unpopular for subtle reasons. It seems, how can you pack so much information into an infinitesimally small thing? That seems unphysical. And so now there are all kinds of wild ideas that maybe you never actually transit into the black hole. Maybe your quantum bits are smeared on the outside, and the surface of the black hole is a hologram for what's on the interior. I think it's just a really exciting terrain to try to understand what's going on at the most fundamental level when we're confronting gravity at its most extreme.
And one idea that I like that some people have criticized, of course, is the idea of physicist Roy Kerr in 1963, where he said that if the singularity were a spinning ring, then you could solve Einstein's equation so that if you fall through the ring, it's like going through the looking glass. Alice's looking glass, you wind up on a parallel universe. And if you go through a second time, you wind up on another parallel universe like an elevator. So you're hitting the up button of an elevator going from one parallel universe to another. Unfortunately, that universe may not be stable, but go on.
Right. No, so it's a kind of extension of looking at the space-time where you extend it as though it can continue over and over and over again in these repeated images through the singularity.
Right.
I mean, in some sense, you know, what does it mean for those to be other universes? Are they large? Are they just like the interior of another black hole? Are they like a Big Bang that has the potential to expand infinitely? I think that it's one of those things where we're conjecturing because we don't really understand how quantum mechanics and gravity at its most extreme come together. So we don't have a prediction, but we can conjecture.
Right. And if you saw the movie Interstellar, there was sort of like a cop-out at the end. Like, where did this wormhole come from? Apparently it came from our future descendants billions of years into the future when they have enough energy to play with black holes. A very cute way of getting around the question of how do you actually build a black hole.
Right. It's like when Stephen Hawking decided to throw a party for time travel, but only sent out the invitations after it happened.
Right.
If you can travel in time, it really shouldn't matter when the invites go out.
Right. That's true.
You could always go back and make it to the party.
Well, personally, I work in string theory. Hopefully one day we'll be able to answer these questions using pure mathematics. Mm-hmm. But right now we should warn the listener that we physicists have no uniform consensus on what happens when you pass through a black hole.
No, but again, the black hole in some senses is one of the only landscapes on which we can work out the tougher ideas in string theory. It's a place on which to try to understand how string theory might solve problems in gravity in general, and the black hole is the testing ground.
Yes, so we actually have an experimental way. And after the break, let's talk about attempts by radio telescopes to actually photograph the event horizon of a black hole. Welcome back to Science Fantastic with Professor Michio Kaku. If you just tuned in, you might think we have two crazy physicists talking about science fiction. However, we're talking about science fact. We physicists believe in things that are reproducible, falsifiable, and testable. And black holes, we think, well, we're going to be able to photograph the event horizon of a black hole, we think, using powerful radio telescopes. So, Jana, tell us a little bit about the black hole at the center of the Milky Way galaxy and attempts being made to actually record the event horizon of this gigantic black hole.
Amazingly, there is a black hole 4 million times the mass of our sun, 26,000 roughly light years away in the center of the Milky Way galaxy, our own galaxy. Technically, we're orbiting that black hole. Just takes us a long time to make one orbit. Our entire solar system, along with the entire Milky Way, is spinning around that central black hole. And we know it's there by looking at the orbits of entire stars around it. And you can see that these stars, in about 16 years or so, rough timescales for one of them, orbits an object that you can deduce from the orbit is 4 million times the mass of the sun, but only fits in a few sun widths across, which is spectacularly small. So we think of black holes as these huge objects, but they're actually, the whole idea of the black holes that they're spectacularly small for how heavy they are. And so we deduce that it's a black hole, but it would be really thrilling to take a picture of it. I mean, that would be really exciting. You mentioned Interstellar. Interstellar has a mathematical model of what the black hole would look like if you could take a picture of it. And what you really see is a shadow, and you see some stuff swirling around it. And that could be what our own Sag A star, it's called, our own supermassive black hole looks like if we took a picture of it, this beautiful shadow. So there's an attempt to make a telescope, one kind of giant Earth-sized telescope, by combining a whole bunch of smaller radio telescopes and using them together all over the Earth to point towards Sagittarius star in the direction of the constellation Sagittarius and take an actual picture. So this is a really exciting project, Event Horizon Telescope, and I'm really thrilled. The data's already coming in, and they're analyzing it now, and who knows, maybe within a few months we'll have a picture.
And for those people who want to actually spot a black hole tonight, go outside, look at the constellation Sagittarius, and in an area called Sagittarius A, that is the center of the galaxy, and at the center of the galactic nuclei, there is this raging black hole. Now, you mentioned that by lashing together all these radio telescopes, we can get an effective radio telescope the size of the Earth. So that should be powerful enough then to actually see the outlines of the event horizon, right? Isn't that incredible?
It is incredible. So what you'd really be seeing is light emitted from around the black hole everywhere except anything that got too close and fell into the event horizon, which would appear dark. And so it really is, it would be the first time we've ever taken a picture of a black hole. Whenever we say we've seen black holes, what we really mean is we've seen mayhem and destruction induced by a black hole on its neighboring companions, sometimes another star, sometimes a bunch of debris swirling around it in a disk, sometimes jets shooting out. But nobody's ever taken a picture of the shadow of the event horizon.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Jana Levin. So, Jana, where we last left off, we were talking about gravity wave detectors. First of all, what is a gravity wave predicted by Einstein himself over 100 years ago?
Yeah, right after Einstein completed his theory of curved space-time, he thought the most important question was the question of gravitational waves. And the idea of gravitational waves is that if you can curve space and time, let's say by something like the sun or the earth or even a black hole, then if that object moves around, those curves must in some sense follow it. And that means that they could create a wave in the shape of space-time, a wave in the actual curves of space and time itself. So gravitational wave is not like a sound wave, which is a wave in a medium, air, but it's a wave in actually the shape of space-time. And this was something that was so hard for people to wrap their heads around that even Einstein kept changing his mind. Are they real? Are they not real? He wasn't sure if they actually existed. And he certainly thought that even if gravitational waves were real, even if there were these waves in the shape of space-time, that these ripples, that nothing could be strong enough, could shake space-time strong enough to create something detectable. He thought that was absurd. And you have to remember that Einstein also didn't believe black holes could form in nature. So it really wasn't until the most kind of extreme objects in the universe are at their wildest motions that you can create something that you would even have a hope of detecting on Earth. And so when this project LIGO began 50 years ago, people were still debating about the existence of gravitational waves and the existence of black holes. And so that's how amazing the aspiration was and the perseverance of the original architects, that they kept going in the face of really not being sure nature would provide. And so they built this remarkable instrument over the course of 50 years that is able to measure the most subtle variations in space, variations over 4 kilometers of less than a 10,000th the width of a nucleus, a proton. And that is what allowed them that incredible sensitivity to detect the ringing of space-time, to record it like a sound. This is not light. This is not taking a picture, but to record it like a sound from the collision of 2 black holes 1.3 billion years ago. It's really an amazing achievement.
Now, sometimes children ask the question, if the sun were to disappear right now, if the sun were to disappear, how long would it take for us to notice it? And I guess if Einstein's theory is correct, it would take 8 minutes. That is, gravity waves travel at the speed of light. right?
Exactly. So right now we're on a curve in space-time. Our orbit is a nice curve in space-time, pretty close to a circle around the sun. If the sun were to disappear, those curves would disappear. And so it would have to be communicated to us by a waving in the shape of space-time, flattening it out. And by the time that wave got to us 8 minutes later, which is the travel time for a gravitational wave, it happens to be the same as the travel time of the speed of light, would flatten it out so that we no longer experienced this circular curve around the sun, and we would simply travel off in a straight line.
Right, amazing. Now,
we'd
also,
be lost in the galaxy.
Also, LIGO, you mentioned, is this gigantic laser detecting device that can pick up gravity wave vibrations from colliding black holes in outer space. But what's next? I understand they picked up now radiation from colliding neutron stars. So what's next?
That was fantastic. Well, the colliding neutron stars was fantastic. Everyone was incredibly thrilled about black holes. Many people did not believe black holes would ever be detected by LIGO. They thought there's just not enough of them in the universe. They collide so rarely. In our own galaxy, they might only collide once every few 100 million years. So we have to be able to listen so deep into the universe that we're able to detect things from millions of galaxies. And that means reaching over 1 billion light years into the universe. And thrillingly, tons of black holes were discovered. It was amazing.
Welcome back to Science Fantastic with Professor Michio Kaku. Well, once again, our special guest today is Professor Jonna Levin, author of How the Universe Got Its Spots, Black Hole Blues and Other Songs from Outer Space, and host of Black Hole Apocalypse. Well, let me ask you a question. What's the meaning of the title, Black Hole Apocalypse?
Yeah, well, it was kind of inspired by the concept that it's ultimate fate for our universe, that everything, it's at least a possibility, that everything that can fall into black holes will, which might literally be everything. I mean, in principle, if we waited long enough, we would fall into the black hole at the center of our galaxy, this 4 million solar mass black hole. It just will take an incredibly long time. I mean, the future is much, much longer than the past. But is an ultimate apocalypse that everything falls into black holes, and that's the end of the universe as we know it.
But aren't we in a stable orbit that is far away from a black hole? Newton's laws of gravity are perfectly valid.
Well, we are also emitting gravitational waves, just incredibly tiny gravitational waves from our motion around the black hole at the center
of our galaxy. So we're decaying slightly with each rotation.
Very slightly. It's just going to take, there's so many other factors on our orbit being pushed and pulled by local things. But if you waited long enough, everything should, in principle, fall into the black hole in the center of our galaxy. Now, the universe is a little less than 14 billion years old, and the future is much, much, much longer than the past. I mean, in principle, we're falling into the sun by the same mechanism as well. We emit some gravitational waves, and we are decaying ever so slightly. But it's much less, for instance, than the actual pull of the moon and the other forces in the solar system.
Now, don't black holes also have a finite lifespan given by Hawking radiation, that the black hole itself radiates Hawking radiation and therefore gets less and less energetic with time? Over trillions upon trillions of years, the black hole will explode. What are your thoughts?
Yes, I think that's exactly the future that we could imagine, is that everything falls into black holes, and then the black holes themselves evaporate away according to Hawking's process of radiating quantum particles, and eventually, as they get smaller and smaller, and when they get really small, they kind of explode. So the black holes cast the matter back into the universe somehow, but by then, everything will be so far apart, the universe will have expanded so tremendously that that debris will just sort of float alone, and the skies will be dark. There will be no more bright skies, no more stars to look at, and we could imagine that as a kind of end of time.
So some people ask the question, why should I wake up tomorrow morning given the fact that the universe is going to die in the far future? Woody Allen, I think, has referenced that. Woody Allen puts cosmology in his films quite often. So what are your thoughts? You think that the universe is ultimately going to die in a sea of black holes and decaying black holes, or what are your thoughts?
I think that is, I mean, again, there's a lot we don't know about the universe. Maybe the current expansion of the universe will slow down because what's driving it, the dark energy, evaporates. I mean, there are things we just don't know. But if things go on as we know now, then yes, that's what I imagine. The universe will expand so much that the skies will go dark, things will fall into black holes if they can, and the black holes will evaporate away. And that is the future. Now, I wouldn't despair because that is so far off. And the sun's going to blow up before then. You know, the sun's going to distend and vaporize the inner planets. And, you know, right now we're not doing too well as a species. I'd be a little bit more concerned about, I don't know, North Korea.
Okay. Now, let's change gears a bit because some people are worried that there could be a black hole that we create on the planet Earth. We physicists, of course, think that's not possible. But some people are worried about the Large Hadron Collider, a gigantic atom smasher outside Geneva, Switzerland. And some people think that maybe it's going to swallow up the Earth. So first of all, what is the Large Hadron Collider, and what are your thoughts about it creating a black hole on the Earth?
Well, I actually think it's a really interesting proposition. So, the Large Hadron Collider is the most powerful collider ever made by human beings, and it reaches energy scales that are only achieved otherwise in very early universe, although we also have some cosmic rays which hit the Earth's atmosphere with a similar kind of power. And by smashing particles together, we, in the debris, can discover new particles that haven't been made since the early universe, things like the Higgs particle, the famous
Okay, John, unfortunately, we've run out of time, but thank you so much for being on Science Fantastic.
Thanks so much, Michio. It was a lot of fun.
Okay, and if you want to know more about black holes, once again, Black Hole Apocalypse is something that you should see. Go to pbs.org for more information. Professor John Levin is the author of How the Universe Got Its Spots and Black Hole Blues and other songs from outer space. And you've been listening to Science Fantastic with Professor Michio Kaku.